In this and the next few videos, we're going to be focusing on design using root locus technique. We've seen examples of the root locus technique being used to evaluate how the system's performance is going to change with the gain. We also saw an example of using root locus to design a system, specifically determine the gain of the system to achieve the desired performance. What we're going to do in this chapter is to expand the root locus techniques to designing a suite of controllers and compensators that are widely used in the modern control system. So our objective here is to use root locus technique to design a controller or a compensator. Then what is a controller or compensator, and how do we use root locus technique to design a controller or compensator? The definition covers both points. A compensator is a component that is added to an existing control system to achieve the desired performance in time response and steady-state error by means of introducing additional poles and or zeros to the closed-loop transfer function. Basically, by adding additional component, which is what we call the compensator, you introduce additional zeros and or poles to the closed-loop system such that the system's performance will be adjusted. The process of introducing a compensator to a control system is often referred to as compensation. Depending on where a compensator is added in a control system, there are two compensation techniques. One is called cascade compensation, in which a controller or a compensator is added in cascade with the original system. The other is feedback compensation. The feedback compensation is achieved by introducing a compensator or a controller on the feedback paths in the original system. Due to the time limit, our focus in this class will be on the cascade compensation. There are in total 4 cascade compensators that we're going to learn in this chapter. The first one, which is the easiest one to understand, is called PI controller. PI stands for proportional integral. PI controller is used to reduce the steady-state error to 0 without affecting the time response. The transfer function of a PI controller always takes this form, with gain denoted as Kc, with a 0 at negative Zc, and a pole at the origin. For a PI controller to work as expected, Zc has to be close to 0 and Kc has to be close to 1. As far as why these two conditions must be satisfied for a PI controller to function properly, I will get into that in the next slide. Here, I want to very quickly provide you the background of where the name of PI controller comes from. Here is the transfer function being rewritten into the sum of 2 terms. The first one is Kc, which is a constant. If you have a system whose transfer function is equal to Kc, such system would be only scaling the input by a factor of Kc. So this first term corresponds to proportional. As for the second term, we have a constant divided by s. We know that division by s in the s domain corresponds to integration in time. Therefore, for a system with the transfer function in this form, it will integrate the input as well as scaling the input. So the second term corresponds to integral. So we can view the proportional integral controller as a parallel combination of integral and proportional, and this is why such controller is called PI controller. Now let's take a look at the reason behind the constraints that we have to apply to the transfer function of PI controller, which is ZC needs to be very close to 0 and KC needs to be very close to 1. Let's start with a system without the PI controller. Here is a third order system with its root locus provided here. Think about why it's a third order system. Well, the reason that it is determined to be a third order system is because if you look at the root locus, we have 3 branches. One branch starts right here and ends at infinity along the real axis. 2 branches start at this point and this point, and these 2 branches move toward each other first, meet at this point on the real axis, and then break away. One proceeds upward, the other one downward. For the third order system, we have the capability of adjusting the gain K. Let's assume that the gain has already been picked out, such that one of the 3 closed loop poles is at this location denoted by A. The second closed loop pole will be down here, which will be the conjugate of this complex point A. The third pole will be somewhere over here to the left of this open loop pole, which makes the point A and its conjugate the dominant closed loop poles, as the third closed loop pole is further away from the j omega axis. This makes the time response of the system to be dominantly determined by the closed loop pole A and its conjugate. Since point A is on the root locus, it has to satisfy the angular property. So we can write that the angle of the open loop transfer function at point A, which is expressed as the algebraic sum of the 3 angles associated with the 3 open loop poles, is equal to alt multiple of pi. I want to elaborate a little bit more on how the angle of the open loop transfer function at the closed loop pole A evolves to negative theta 1, negative theta 2, and negative theta 3. According to the root locus provided down here, we know that the open loop transfer function g of s has 3 finite open loop poles. To write the transfer function g of s, I'm going to introduce negative p3, negative p2, and negative p1 as the 3 finite open loop poles. And the transfer function g of s becomes, then the angle of the open loop transfer function at the closed loop pole A can be written as the angle of A plus P1 is the angle of the vector pointing from negative P1 to A, which is basically defined here on the graph as theta 1. The angle of A plus P2 is the angle of the vector pointing from negative P2 to A, that's our angle theta 2. Angle of A plus P3 is the angle of the vector pointing from negative P3 to A, that's angle theta 3. Now we have a pretty good understanding of our uncompensated system, or the system without PI controller. Then let's talk about our design objective. Our design objective is to reduce the steady state error to 0. We know that this is a type 0 system. For a type 0 system, the steady state error due to step input is finite non-zero. And we want to reduce this non-zero finite steady state error due to a step input to 0. To reduce the steady state error due to a step input to 0, we need to change the type of the system from type 0 to type 1, which requires an S factor to be added to the denominator of the transfer function on the forward path. Here is the system that has an integral compensator added in cascade with the original system on the forward path. By adding the integral compensator, we basically introduce an S factor to the denominator of the overall transfer function on the forward path. With the integral compensator, the system now is a type 1 system, which will for sure have zero steady-state error due to a step input. However, the additional component added to the system is also introducing an additional open loop pole at origin, which makes the system's order now a fourth order. It also increases the number of branches on the root locus to 4, and more importantly, it changes the shape of the root locus. Due to the change in the shape of the root locus, point A is no longer on the root locus because it does not satisfy the angular property anymore. This implies that the new system will not have the time response that is associated with the complex point A. The time response of the system with the integral compensator is different from that of the original system. So the problem we're dealing with right now is that we need the integral compensator because we want the system to be a type 1 system. But on the other side, the additional open loop pole at the origin changes the root locus, and therefore the time response of the system changes. If we can figure out a way to compensate the effect of the additional open loop pole at the origin on the root locus, then the problem we're dealing with right now will be resolved. Then how do we compensate or counteract the effect of the open loop pole at the origin on the root locus? We can actually draw some inspiration from this angular property equation. We have the angle of the open loop transfer function, including the integral compensator, evaluated at the complex point A, equal to the algebraic sum of 4 angles. According to the previous slide, negative theta 1, negative theta 2, negative theta 3 is equal to odd multiple of pi. This means that what makes the algebraic sum of the 4 angles not equal to odd multiple of pi is because the angle theta c. If we can introduce a positive angle to the algebraic sum that is almost equal to theta c, then we can bring the algebraic sum of the angles, now it's going to be 5 angles, back to the odd multiple of pi, making the complex point A on the root locus. So to counteract the effect of the pole at the origin on the root locus, we're going to introduce an additional open loop 0 that is close to the origin. Here is what the root locus will look like with an additional 0 at negative a. So we'll make negative a to be very, very close to the open loop pole at the origin. Then we would have the angle associated with the open loop 0 at negative a to be very, very close to the angle associated with the open loop pole at the origin. Then the algebraic sum of the 5 angles, that is going to be the angle of the open loop transfer function evaluated at the point A to be almost equal to odd multiple of pi, which will make the complex point A on the root locus of the new system that has additional open loop 0 at negative a and additional open loop pole at the origin. By adding an s plus a factor to the numerator of the compensator, the integral compensator evolves to a PI controller. Now I'm going to use example 9.1 to demonstrate the design process for a PI controller. Here we're given with the system which has already been designed to have 16.3% overshoot by setting the gain to 19.7. In the table below, I've already gathered some of the basic but important information about the uncompensated system. If you set the gain of the system to be 19.7, using MATLAB, you can find the closed loop poles. There are 3 closed loop poles. 2 are complex, closer to the j omega axis. They are referred to as the dominant closed loop poles. The additional one, which is the third one, is at negative 5.62. The system doesn't have closed loop 0, so I put none in there. As far as the second order approximation, the decision was made to be no, because the additional closed loop pole does not really satisfy the 5 times rule of thumb. This system is a type 0 system, so the evaluated static error constant is the position constant, which comes out to be equal to 1.643. And this is calculated with the gain, again, equal 19.7. I did also a simulation in MATLAB. I found out that the steady state error is 0.378. 0.622 is the final value of the step response in the simulation. The percentage overshoot comes out to be equal to 14.6, which is different from the specified percentage overshoot of 16.3%. The reason why the simulated percentage overshoot is different from the desired percentage overshoot is because the gain of 19.7 was found to make the dominant closed loop poles to have 16.3% overshoot, while at the same time, the third pole does not satisfy the 5 times rule of thumb, so the time response of the system is also affected by the third pole at negative 5.62, resulting in a percentage overshoot different from 16.3% associated with the dominant closed loop poles. What we're going to do for this system is to design a PI controller such that the steady state error of the system is going to become 0. We've already discussed that this system is a type 0 system. It has non-zero steady state error due to a step input, which was found to be 0.378. If we want to make the system to have 0 steady state error due to a step input, then we need to make the system a type 1 system. Placing a PI controller on the forward path in cascade with the gain and plant will achieve this goal. There's really not much to design. We just need to make sure that the transfer function of the PI controller is going to take this form, and the gain of the PI controller needs to be almost equal to 1 or equal to 1. And the 0 at negative ZC needs to be very close to the origin. Here is the system with the PI controller already placed in cascade with the gain and the plant. I have already chosen the gain for the PI controller to be equal to 1, and we just need to discuss the value that we need to pick for ZC. We want ZC to be close to 0, so we may be able to start with, let's say, 0.1 or even negative 0.1. Can we do both, or is there one that we should avoid? Let's have a discussion on the sign for ZC. So when ZC, here denoted as A, is positive, then the open loop 0 will be in the left half plane. Then the branch that starts at the open loop pole at the origin ends at negative A will be in the left half plane. But if ZC, which is A in this case, is negative, then that means open loop 0 at negative A will be now in the right half plane. Then this branch starts at the origin will be ending on the right half plane, making this entire branch in the right half plane corresponding to a closed loop pole always in the right half plane. So the system will always have a closed loop pole in the right half plane, and the system is unstable. So when you choose the value for ZC, or A in this case, you want it to be always positive. Okay, then we're going to choose 0.1 for ZC. So that's our PI controller. We're done with designing the PI controller. We're going to move on to step 2 to analyze the compensated system. I'll start with writing the open loop transfer function of the compensated system, which is denoted as G sub C of S. The gain comes from our original system. This is the PI controller. This part is also from the original system. We're going to simulate the time response of the compensated system in the MATLAB. I have already defined the gain of the system, which is equal to 19.7, and also the transfer function for the plant, G, and I'm going to define the PI controller. The PI controller has a 0 at negative 0.1 and a pole at 0. So here is the PI controller. The open loop transfer function of the compensated system is equal to the gain K multiplies with the PI controller and multiplies with G. And closed loop transfer function after compensation is equal to, I'm using feedback command to determine. All right, so that's the closed loop transfer function of the compensated system. If you use the step command, you can find the step response of the compensated system, which I have already included in the packet on the same graph with the step response of the uncompensated system. Here we have the blue curve representing the step response of the uncompensated system with a finite non-zero steady state error and a percentage overshoot of 14.6%. The orange curve is the step response of the compensated system with a final value of 1, indicating 0 steady state error. As far as the percentage overshoot for the compensated system, it is equal to 0 because there is no overshooting above the final value of 1. This seems to be against what we'd expected, which is that the time response of a system should not be affected by a PI controller. But if you take a look at the initial trajectory of the step response of the compensated system, which pretty much follows the trajectory of that of the uncompensated system, but after the initial hump, it has to continue to grow toward 1 in order to produce a 0 steady state error. Now we're able to confirm through the simulation that the compensated system has 0 steady state error. The time response of the compensated system tries to follow the trajectory of that of the uncompensated system, but then has to continue to grow for an extended period of time due to the significantly raised final value. To finish up, I'd like to go back to the table to fill in that information about the compensated system. So the overall gain of the system is not affected by the PI controller. We still have 19.7. The dominant closed loop poles, the additional closed loop poles, and closed loop zeros, we can find those in MATLAB. For Kp, which is the position constant, we have a type 1 system, so the position constant is equal to infinity. The steady state error was verified according to simulation equals 0, and the percentage overshoot is equal to 0. Let's quickly go back to MATLAB to find the closed loop zeros and poles. I have the closed loop transfer function TC, and I can use 0 command to find its closed loop 0, or you can just eyeball it. It's equal to negative 0.1. For the poles, I'm going to use pole command. So I have 4 closed loop poles. I have 2 complex closed loop poles at negative 1.16 plus or minus J 2.02. They are the dominant closed loop poles. The additional closed loop poles are negative 5.61 and negative 0.065. For second order approximation, we're going to have to look at the pole zero locations. So we have dominant closed loop poles right here. We got a closed loop 0 at negative 0.1, which is fairly close to a closed loop pole at negative 0.065. So we have this closed loop 0 and closed loop pole satisfy cancellation. The other additional closed loop pole does not satisfy the 5 times rule of thumb. So we cannot say that this fourth order system with the PI controller is a good second order approximation. The PI controller we chose is the one that has a 0 at negative 0.1. I'm sure some of you are probably wondering, would a different value work? Well, that's a very, very good question. I'm actually going to use the last few minutes of this video to do a comparison study between two PI controllers with different zeros to demonstrate the pros and cons when it comes to choosing the zero for a PI controller. Here's the same plot that we discussed in the packet, the blue one being the step response of the uncompensated system, and the red one is for the compensated system with a PI controller that has a 0 at negative 0.1. And now I'm going to use a different PI controller. In this PI controller, let's call it a MATLAB G PI2. It's going to have a 0 at negative 0.01. The open loop transfer function of the compensated system with this different PI controller is going to be equal to K multiplies with G PI2 and multiplies with G. So this is the compensated system with a new PI controller with the 0 that is even closer to the j omega axis. Finding the closed loop transfer function for this compensated system, and we can plot the step response on the same graph. All right, so let's see what we have. This yellow curve is the step response of the compensated system with the PI controller that has a 0 at negative 0.01. For a system with such PI controller, it takes much longer time for the step response to rise to its final value of 1. But if you zoom in on the initial trajectory, the system with the PI controller that has a 0 that is closer to the j omega axis, which is negative 0.01, follows the trajectory of the uncompensated system much more closely, as opposed to the other one with the 0 at negative 0.1. So here is the trade-off with the 0 of the PI controller. The closer the PI controller's 0 is to the j omega axis, the better the trajectory of the time response is preserved. However, the price you're paying is that it takes much longer time for the system to settle in its steady state. So the settling time is significantly increased.